Okay, we're going to look at a couple of examples using the other part of the fundamental theorem of calculus. So many students, when I ask them about the fundamental theorem of calculus and they're taking a class after Calculus 1, remember this part that I have written first here. In some textbooks that's called Part 1, and in other textbooks that's called Part 2. But this is the part that you use to actually evaluate definite integrals, find an antiderivative, and evaluate at the endpoints. So we've already looked at a couple of examples like that. But this other part, often students don't remember. They probably just haven't done as many problems on it. This is a theorem, or part of the theorem that you will use maybe not so much in actually calculating things, but you're going to use this idea in other things related to definite integrals if you keep going in calculus. All right, so let's look at this theorem a little bit, and specifically at this last part that I have written here. And then we're going to look at this example problem and talk about using this second part of the fundamental theorem of calculus with this example that we have here. All right, so it says, first of all, I need a function f, little f, that is continuous on an interval. Okay, then, all right, if I look at this notation here, this means derivative with respect to x. Derivative with respect to x of whatever's after that. So notation-wise, this means I'm going to find the derivative with respect to x of this definite integral. All right, and then this definite integral is from a, that would be the left endpoint of our interval, to a variable x. So instead of being an integral from a to b, we have an integral from a to x, where x is a variable that we are differentiating with respect to. Of f of t dt, then that is all equal to just f of x. So one important thing here to notice is that that is not an antiderivative function. That is just the same function, little f, not little f and capital F like in this other part, but little f and the same function, little f here, but evaluated at x. Right, if we think about why this part of this theorem should make sense, you might think about, in the intermediate step, this antiderivative function, capital F of x. So if I were able to find an antiderivative function, capital F of t, then I would plug my limits of integration in. X is a variable. I would get capital F of x minus capital F of a, and then differentiate with respect to x. The derivative of the antiderivative should take you back to the function that you started with. So one important idea about this is this idea of differentiating, undoing integration even for definite integrals. Okay, so we're going to use that theorem on this problem, and these problems often seem so easy that students don't understand why they're even doing this or what it is telling them. But for this one in particular, this is really just a direct application of this second part of the fundamental theorem of calculus. Our function in this case is e to the t squared. F of t equals e to the t squared, which is continuous everywhere. Continuous everywhere. So we are interested in differentiating with respect to x this integral whose upper limit of integration is x. So that's important to note that those are the same there. And I have a definite integral of this function, e to the t squared dt. Sometimes I have students who try to solve this problem by actually finding an antiderivative, plugging in these values, and then differentiating. That's not going to work for this one. You're not going to be able to write down a closed form antiderivative for this function. I intentionally chose this problem so that that would not be the case. So you cannot write down a closed function antiderivative for this function and do it that way. You really have to do this problem using this theorem. But if I just look at what this theorem says, it says, well, the same function, e to the t squared, but that function, instead of being evaluated at t, now evaluated at x. Now evaluated at x. So if I just pay attention to what this theorem says and match it up with everything I have here in this problem, well, you write down the answer pretty easily. And like I said, some students think that they're not even doing anything here. Right? I've just got the same function I had here, but now evaluated at x instead of at t. And that's the answer for this. And it seems sort of like you're not doing anything. And it is a little less satisfying perhaps than what you might be getting from the other part of the fundamental theorem of calculus, where you get a number at the end, and you can draw a picture and show what that number represents. But this is important for a lot of theorems later. So the key idea here, the differentiation with respect to x undoes this integration with the upper limit of integration being x. This essentially establishes that this function has an antiderivative, whether I can write it down or not, so that then I can differentiate it. All right, we'll look at one more example that's just slightly more complicated than this, but really this is not hard once you know how to read this, read the theorem and do what it says here.